Counting. This is work that's done jointly with Mickey Aitai. It has a kind of funny history, which I will explain. But before I start my talk, I want to start by paying tribute to Mickey Aitai, who recently retired from IBM Almaden. So I think of this talk more as a tribute to him. Of course, he's enjoying his retirement. And we know that Mickey has done some fundamental path-breaking work in many different areas, including circuit complexity, time-space trade-offs, branching programs, lattices, data structures. In some sense, every topic that's either in this workshop or even in the workshop in the parallel program, Mickey has had left a huge imprint there. But actually, he was also interested in very practical questions. So one of the most successful patents in IBM was something that had to do with differential backup, this is before the days of all this time machine and things like that that people use on their Macs, for example, for backup. So he had a very successful patent in that, and I actually happened to look up his patent portfolio, and it turns out that he also has a patent on a mechanical Towers of Hanoi puzzle, which I didn't know about. So and in some sense, the streaming thing that led to this particular question. So he was actually interested in streaming questions as well. And in fact, it was in the context of working with him along with Ravi and Ravi Kumar and Shiva Kumar that sort of this question arose. And that particular streaming work had to do with, arguably the first streaming problem where the order of elements matters. So it's some measure of sortedness. So one thing that always stuck with me is that, I would talk to Ravi and Shiva about, how is it that he actually comes up with these, statements in his papers that, seems so hard to parse, even the statement of dilemma. And the statement that Ravi said was, most of us tend to think in sigma 2. Mickey starts with sigma 4. So I think that's the most apt thing to say about him. So the work I'm presenting in some sense is anachronistic because this thing was done almost 10 years ago or more than 10 years ago, and primarily by Mickey. And we have some further improvements. But we have actually none of this has actually been written up, and in some sense maybe I should have waited before all this is done. But then I thought, this workshop is probably the most appropriate to actually present this thing. So a disclaimer is that the problems, since it's so old, it is possible that what I'm claiming today may actually already be known through a combination of some previous work. So if that's the case, please come and talk to me at the end of my talk. I think I tried to do a fair assessment myself of whether the problem is still open, and so at the very least, anyway, the proof I hope is at least interesting, even if the result you feel is not new. Okay, so let me start. So counting in a stream. So this is arguably the oldest problem in streaming. I mean, going back to a 78 paper of Robert Morris for approximate counting. And the interesting thing is that it's a randomized or probabilistic algorithm that uses space log n. And all I need to tell you about that algorithm is, come up with a random variable such that the expected value of 2 to the x, or x is a random variable, is c plus 1, where c is the number of ones in a stream of length n. This problem continues to have interest for various reasons. So there is recent papers include a floating point version of this particular algorithm. And also, surprisingly, applications to flash memory, where the important thing about this algorithm is not as much the fact that it actually approximates decently. I mean, that's good, but more importantly, that you make very few updates to the probabilistic counter itself. So, and in flash memory, you care about how many writes you make, because each time you write, it degrades the performance of the memory. So anyway, it continues to still generate interest. And also, it has led to this beautiful work in analytic combinatorics, starting with the work of, Philip Flageolet and various others. I'm not listed all the people here. And interestingly, Flageolet sort of got interested in this problem because somebody from IBM San Jose at that time, this is even before, which became IBM Almaden later, contacted him and told him they want to implement this, but there's no proper analysis. So he started with that, trying to analyze this, and that's what led to his own beautiful work on, distinct elements and, hyperlog and that line of work. So, okay, so having said everything about the sort of probabilistic case, so what about deterministic algorithms? Okay, so we know that, this is the way people usually motivate this thing, is that, okay, I can, if I want to count it exactly, I need, log n space because there are n plus 1 values to output. So let's do probabilistic, right, and reduce. But you can ask, what happened if I want to still use only deterministic algorithms and I want to give some multiplicative approximation. So this information theoretic bound is not enough because there are only log n values to output. So it seems like that will give you only log n. So yeah, so that's going to be the subject of this talk. Now, if you say, okay, I only care about uniform algorithms, so just think of it as, uniform not in the traditional sense, but more in the sense that you have an automata, but you're not counting time explicitly, then this question apparently was not solved until somebody recently observed that actually there's a simple argument that gives an omega n lower bound for this case. So uniform is basically finite automaton, and I'll describe this argument adapted to our settings. So what do I mean by this thing? So suppose I give you an automata, and I'm supposed to count the number of ones in the stream, or approximately count the number of ones in the stream. So suppose the number of states is, say, only at most n to the 1 over 16. So you are trying to prove a log n lower bound on space. So suppose the states is number of states is very small. Then sort of, it's a very simple thing. So you start by, feeding this automaton a lot of zeros until it starts to cycle, right? So let me go back. So you feed it zeros until it starts to cycle, and then you feed it a bunch of ones, and it then again starts to cycle. I've drawn it in a manner that these states are distinct from these states, but they need not be. It's just convenient to view this picture this way. And then what you do is you try to find sequences so that the amount of time spent in this cycle is equal to the amount of time spent in this cycle, and you just maximize this thing. So on the one hand, by spending a lot of time on this cycle, you have too many zeros, and spending a lot of time on this cycle, you have too many ones. So you can basically produce these two states where, on the one hand, the count I is at most n over 8. On the other hand, it's at least 7n over 8. So you actually get the lower bound that you need. Okay. So now the question is sort of what happens with non-uniform algorithms, and that's what I'm going to be talking about. So what do I mean by non-uniform? Is basically branching programs. Okay, so we've all seen branching programs in several talks, but in this case, it's actually a very restricted type of branching program referred to as OBDD. So it's basically a leveled branching program, and it's oblivious because you read the same variable in each time step, and it's read once. Right. So in fact, interestingly, when I was initially working on streaming, I think it wasn't then very fancy or popular then people would ask me, isn't this just OBDD? Why are you doing streaming? Okay. What's so cool about it? So anyway, so yeah, but in terms of actually proving lower bounds, yeah, we are in some sense thinking about OBDDs. So, okay, right. So that's the sense in which I'm saying it's non-uniform. Now, does non-uniformity actually help? Well, at least for the instances that I gave earlier, non-uniformity can actually help distinguish these two sets of inputs. Remember I said there are the zeros followed by ones in both cases, but it's just that the number of zeros is huge here and number of ones is huge here. So certainly you can distinguish these two classes of inputs by a very simple OBDD. Just check the value at the middle, right? So in some sense, yeah, so the value at the middle will be that in this case it will be 0 and in this case it will be 1, just by the nature of the inputs that are constructed here. And basically this is saying that you can actually use, another way to state this is that you can actually use the clock to your advantage. So basically by saying that I'm checking the value at n/2, I'm basically saying, okay, look at the clock as a counter and wait until the most significant bit becomes 1, and at that point check the input that you're reading. Okay, so it's a very simple use of the clock, and I couldn't sort of resist the temptation to sort of present this other cute algorithm due to Parikshit and Jaykumar that actually uses the clock in a more sophisticated way. So let me just present this thing. I mean, it's cute enough that I thought I'll talk about it. So yeah, you're interested in finding duplicates, and your domain is of size m, but the stream length is really huge. It's of size 2 to the m. And the way the algorithm works is that you basically use the clock itself sort of to remember the elements that you have seen in the stream so far. So a 1 at a particular position indicates that you have seen this element sometime in the past. Okay? But it's not an if and only if things. Like, there are no false positives. If you see a 1, then certainly if a bit is set to 1 in the clock, you've certainly seen it before, but you're not remembering all the elements that you have seen before. So, but certainly that invariant is going to be maintained. And you can see what happens is that, okay, when you read the current symbol, because of the invariant, if the clock at that particular j is equal to 1, then because of the invariant, you have seen it before, and therefore you have found the duplicate, right? So otherwise, it's 0, okay? And what you're going to do is, you are going to advance the clock until that particular position becomes 1. Now, this is always guaranteed to work because of the stream length being huge. N is at least 2 to the m. So the clock will, at some point, get to the point where clock of the jth position is equal to 1. Now, during this process, okay, what happens is that, okay, you have a 0 here, and to the right of it, is a bunch of 1s. And as you're waiting for this 0 to turn into 1, all these 1s become 0s, right? So you are forgetting things that you have seen before, but you're never introducing a false positive. So when it actually at the end ends up becoming 1, you are, in fact, maintaining that invariant because, in fact, before this, when the loop started, you had actually seen this before. So, and this is since this is the only place where the program can actually terminate, this actually produces the correct answer. So non-uniformity in this case actually helps in a very big way.
Sorry, how is this implemented as an OBDD? What's clock here?
Basically, okay, maybe in this example you can see the clock. When I said look for the most significant bit to be 1, that's like saying wait until you're looking at xn/2.
Just a particular layer of your
particular layer. So the clock, when you're doing tests on clocks, you're basically saying in these layers are special.
Okay.
Does advance the clock mean just read elements from the stream and throw them away?
Yeah, throw them away.
Just guaranteed to find some duplicates?
Yes, because the only place that this algorithm can terminate is here. Because of the stream length is large. That's crucial. So it cannot terminate. This will not abort because this is not like a bad statement here. This will certainly succeed. So the only place, because there's a loop here, the only place that it can terminate is here. It is guaranteed to terminate because the stream length is finite. So it has to terminate somewhere.
But why doesn't it run out of the stream?
because where can it run out, right? The only place it can run out is here, where it says, hey, I don't have any more elements to check. But this is always guaranteed to work, because if the clock at that particular bit is 0, at some point it will become 1, because the stream length is at least 2 to the m. So it's quite a simple but clever use of the clock. So anyway, this is not relevant to what I'm talking about, but I thought, I should just tell you that clocks can be used cleverly, although I don't know if there are any practical uses of such things. Okay, famous last words.
So this is like a width 2 branching program or something like that. So it's
certainly you have, no, it probably width a log m, because you have to remember the current symbol.
I see.
Right. But I think the thing that the point is that I think if for general duplicate finding, when you don't have, can't play such tricks, you will need linear in m or something like that. Right? Log n, which is like, poly in m or something like that. In this case, you can actually get log m. Okay, so anyway, with that, being mentioned, let me then describe the main result of this particular talk is that any OBDD that actually 2 approximates the count needs space, omega log n. So that's the result I want to present, and I hope to present the proof in its entirety, because it's quite simple.
By space log n, you mean width n?
Width poly in width, say log to the 1/3 n or something. No, I'm sorry, no, width n to the 1/3, right?
Yeah.
Space, right? Yeah. Okay. So even though I'm talking about 2 approximation, the result actually, just works even for multiplicative n to the delta approximation. And I won't mention this thing, but it is the lower bound technique works for something more general called monotonic counters, but I won't define what that is. Okay. Right. So the result is clear now? Okay. All right. So what I want to do now is I want to give some notation and then dive into the proof. So okay. So I'll start with this notation of an interval. Basically, I look at every node and look at all the possible counts that reach that particular node. Okay. Now, in general, this need not be an interval, right? That it can miss some of the elements in the middle. But all I care about is the minimum and the maximum of the counts that are reached there. And saying that it's an interval is just a convenient way to talk about properties of that, rather than having to say for the minimum this holds, for the maximum this holds. It's just a convenient way to state things. So for example, at the root, it's going to be 0, 0. And look at this particular node. So this branching program, I didn't mention earlier, computes parity. So at this particular node, you should get all the inputs that have parity 0. And this column, it's all about inputs that get parity 1. So here, the valid input should be only 0 and 2. But since I'm throwing away information about things in between, so I'm just saying it's an interval from 0 to 2. Right? Okay. And so that's an interval reaching a node. And at each level or each time t, I only care about the maximal intervals at that particular level. So in this example of, again, at this particular level, so the ones that are in red are the ones that are not maximal. Because in this particular layer, you see that 0, 2 subsumes as 1, 1. So I don't care about these intervals. I only care about the maximal intervals. And of course, the number of intervals at any particular level, or number of maximal intervals at any particular level, is sort of a simple, gives you a way to bound the space. So lower bound the space. So anyway, so I'm interested in counting how many maximal intervals they are there in each level, and in particular show that there must be some level where there's a lot of maximal intervals. Okay. So what are some simple properties of this is that if you know that there is an interval KL at some node, if it's an interval at time t, meaning that it's some node is labeled by that particular interval, then at time t plus 1, there must be an interval containing kl, and there must be an interval containing k plus 1l plus 1. This is simply due to the fact that, if I'm at this, say, this node out here, right, and I read a 0, right, then this node here will certainly get the smallest and the largest. It may get more than what's there, than just the minimum and the maximum. But the statement is that it contains KL, and that's certainly true. And the same thing holds because when you read a 1, the same thing happens, is that, since K and L are the minimum and the maximum, when you read a 1, you will be getting K plus 1 and L plus 1, but there may be other stuff that reaches there. Okay. So it turns out that for the rest of the proof, I could have just done this thing. Once I've done this thing with stating a family of intervals, one for where in each level, or rather a family of sets of intervals, right? Each level has a certain collection of maximal intervals, and I have one per time or one per level. And I could have just proceeded with the rest of the proof just purely as a combinatorial exercise looking at this particular family. But I will still stick with the branching program sort of intuition, because it's easier to reason in what I'm presenting. Okay. So, right. So, okay. So this is perhaps the most important notion here. So it's the notion of disappearing counts. So we say a particular count k is present at time t, right? That if it turns out to be the left endpoint of one of the maximal intervals at time t. So there is some interval k comma l, which is maximal for some l, and k is sort of the left endpoint. So when I say k is present, I mean k is the left endpoint. So when I say present, think left endpoint. Okay. So one comment is that 0 is going to be present at all times because it is sort of the boundary, right? You cannot go smaller than it. So there must be always something that has 0 as a left endpoint at all time. Okay. All right. Now, count k disappears during time t if it is present at time t, but it's actually absent at time t plus 1. It's not present there. Okay. So this is sort of a natural notion that says that, hey, this is going to be bad for me in terms of approximation because it was present at time t, but I seem to have lost the information that I read a 1 because there's no interval in level t plus 1 or time t plus 1 that has k plus 1 as a left endpoint. So these are times in which something bad has happened, right? So I was trying to think of a nice picture to draw here, and the closest I could think of was to draw a picture of Dracula. Certainly is a count, and he keeps appearing and disappearing in the movies. So but it was too cute to put it there. So anyway, but the important thing to remember is it's present at time t, but absent at time t plus 1. Okay. So the main lemma is that suppose that these counts cannot actually disappear too many times, okay? And so if a count k disappears d times, d is positive, then at termination there is an interval containing k, need not be the left endpoint, but it's an interval containing k, whose right endpoint is at least k plus d, okay? So of course, if you're interested in good approximations, then you cannot allow d to be too large, because given an interval at the end, it's a large interval, so the minimum is this, maximum is this. What are you going to output, right? Because it's output at something in the middle or something in the left or on the right, doesn't matter. It's like going to kill your approximation. Without loss of generality, let's assume you only output the value which is the minimum of the counts that reads. Okay. So this is trying to say that, if you had a good approximation, then you cannot have it disappear too many times. So let me talk about the proof of this thing. Okay, so I'm just going to illustrate this proof for the case that d equals 2. So this is probably the most technical of all the slides, but it's quite simple. So suppose so this node in purple is one of those places where k disappears. That it's present in this time step, but it's actually absent in this time step. So I claim that, okay, so KL is an interval at this particular time step, at time, that's at time t. At t plus 1, I claim that there is an interval I1 that contains k comma L plus 1. So let me run through this argument. So by the property I mentioned here earlier, that if I read a 1, there should be certainly an interval at level t plus 1 that contains k plus 1 and L plus 1. But you read a 1, so k plus 1, L plus 1. So something out here contains k plus 1, L plus 1. And I'm cheating slightly by saying that it's the node exactly where I read the 1. Never mind. So I1 certainly contains k plus 1, L plus 1. But because it disappears during time t plus 1, it cannot be the case that k plus 1 is the left endpoint. So it must be that it actually also contains k and L plus 1, right? So here's an interval that contains now k and L plus 1. And then what we do is we run this branching program by feeding it a bunch of zeros until we hit the next time where k does again this disappearing act. Okay, it's present here but absent here, right? So in that case, what happens is that, okay, so you're reading a bunch of zeros, you have an interval that contains k and L plus 1, but because you're feeding it only zeros, there must be some interval J1 that contains k and L plus 1, because you're not done any changes. But you can, of course, add more stuff. That's why it's always containment. Okay. So what have we done here? We have done here is that it's at the first time it started was KL. Now we have a new interval with k containing k, and its right endpoint is at least L plus 1. Okay. Now we have to repeat the same argument again, but to repeat the argument again, I need an interval whose left endpoint is k. But fortunately, I'm in a time step where k is going to do its disappearing act, so it actually appears here, right? So there must be some other node here where k is the left endpoint, okay? And L prime says it's right endpoint. Now here's where maximality comes in, because it's also a maximal interval. It cannot be that L prime is smaller than L plus 1, because then this interval would be strictly contained in J1. So maximality ensures that this interval also strictly contains k L plus 1. So what we have achieved is that from KL we went to k L plus 1. We have sort of increased the right endpoint by at least 1. And then you keep repeating this argument.
So maybe I missed something. So you're saying you don't look at the intervals for all the nodes? Only for nodes for which they are maximal inside their specific time step?
Right. Okay, so this picture is somewhat misleading, because when I say 1, there's an interval that contains k plus 1 L plus 1. It need not be this node, because this may not be the one that's maximal. It's maybe sitting somewhere else out here. So these arrows are just some sort of misleading in that sense. But yeah, maximality does play an important role here. Okay. All right. So okay. So again, so this was the lemma, right? That there was, if it appears at least d times, then if it appears d times, then there's an interval whose right endpoint is at least k plus d. So all we need to do is, put this all together, and the best way to describe what the strategy is in the header. So you fix a set of counts. In this case, it's going to be just 0 to n to the 1/3. And the previous lemma said that because of the multiplicative approximation, k cannot appear too many times. So rather disappear too many times. Because if it disappears too many times, then its right endpoint will be at least 2k, and then we'll be violating the 2 approximation. So a count k can disappear at most k times, and then a union bound says that the number of times during which some count in C disappears is at most n to the 2/3. There are n to the 2/3 values. Each one of them can disappear at most n to the 1/3 times, so it's n to the 2/3. So therefore, by pigeonhole principle, there is a contiguous block time of length n to the 1/3 during which no count in C disappears. So this is a very standard thing. I went a bit fast over this. But to finish up, given that contiguous block of time where no count from C disappears, you can basically construct this branching program. So I'm almost done, so let me just finish this, and there's one more slide. So the idea here would be that you start with that a node there where the left endpoint is 0, because 0 is present at all times. As you feed zeros, you will always see some interval where 0 is the left endpoint. And then you say that, oh, okay, because 0 did not disappear, there must be an interval containing 1 as the left endpoint. And similarly here, in this time step, neither 0 nor 1 disappears. So there must be 1 with 1 as the left endpoint and 2 as the left endpoint, and so on. And so at time n to the 1/3, because that's the length of the block, you have lots of intervals. Okay, so let me finish up by saying something else, because so this problem of approximating the count certainly has been considered in other contexts as well. So for example, if you allow negative counts, it is known that the space required is actually omega log n. So I mean, this is due to a sequence of 2 papers with these authors. I think Ely and David are in both papers. And what they show is that it's a beautiful result that applies to a very broad class of problems where they say that linear sketches suffice for turnstile streaming.
I have a question about the last slide ahead. So I agree that this block of n to the 1/3 will get all the values, but it might be somewhere in the middle.
Yes.
So why is this a violation of the 2 approximation?
So there's no violation of the 2 approximation at the moment. All I'm trying to get here is that there are lots of intervals at a particular level.
Okay.
The violation of the thing has already been used in the earlier part. Okay, so right, so they suffice for turnstile streaming, but this critically depends on negative counts, and it does not hold in our setting, because if you want to check, say, if the count is 0, what does that mean? You want to check that all the bits in your stream are 0, right? That's a very easy check to do. But if you apply linear sketching means computed mod a small number of primes or counts. Okay, then what happens is that if the modulus, the LCM of all your things is not at least n, then there will be at least 2 values which have the same sketch. So therefore, linear sketching doesn't help in this case. So, but it turns out that actually linear sketching could be useful. So there's an earlier branching program result that tells you how to compute branching programs for majority, and those branching programs can actually be used to give polylog n space, but you need polylog n passes. Now, admittedly, this is, I think, non-uniform and can be made uniform, but I think I'm fairly confident, but it's to be determined. Okay, thank you.
No questions? So you said that the same law one works if you get n to the delta approximation. So do you know what happens if you want even a weaker approximation? Like there's some sense where you could use even low space?
Right. So that's one of the things that I mentioned. We are still, work like in something like n/4 to n/2 or something like in the very high counts and 2 approximation. Yeah, that's still open. I think we have some ideas that can handle that case too. You have to be careful there again because of this clever use of clocks. So here we are mixing zeros and ones, right? When you have very high counts, you want to still make sure that mixing happens. So I think this argument will not work for sure. So we have, I think, a different argument, but I think the fault is probably is mine because I have not written it up, and so it's not Mickey's fault, it's mine. So anyway, I hope to get this done, soon. So stay tuned. Thanks for the question.
Is it known that there is a trade-off between number of passes and the space? I mean, because your result seems it's not possible to move it farther for many passes. Is that no?
Yes, right. So there's an issue of randomized versus deterministic. I think most people care about randomized. So you're asking about deterministic.
Yeah, for example, for this.
Right. Yeah. So I don't know what the trade-off is, and I'm just saying that probably people haven't studied this question in detail. At least as far as I know. So yeah, there's somewhere there's some transition happening to polylog n space from log n space. But admittedly, okay, so yeah, so this is all in this non-uniform setting.
Polylog log n.
Oh, I should say polylog log n. Yeah, sorry, my bad. I should say log n space. So okay, this is a bad statement. So right, is it all polylog log?
Or it's just order log log.
I think everything is order log log.
Yeah,
Okay.
those should both be log log.
I think they both should be log log. My bad.
It's the author of the paper.
Right. Yeah, it's a question of translating the bounds from here to the setting. So I might have messed up.
Explain Jayram.